This is SpaceTime Series 25, Episode 90. Coming up on SpaceTime, the red supergiant Betelgeuse blows its top. Could Earth's continents have come from outer space? And bound for the moon, NASA's Artemis 1 rocket rolls out onto the launch pad. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have now concluded that the sudden dimming of the semi-regular variable red supergiant star Betelgeuse back in 2019 and 2020 was caused by blowing away a massive chunk of its stellar surface. You may recall back then the event sent alarm bells ringing around the astronomical community. Suddenly the ninth brightest star in the night sky had dimmed down to the 20th. And speculation abounded whether Betelgeuse was about to go supernova. Initially, astronomers were unable to explain the strange event. Betelgeuse regularly pulsates, but not to this extent. This was completely unprecedented. Eventually, astronomers discovered the dimming was caused by a massive cloud of dust blocking out much of the star's light. But where was the dust from? And if it was from Betelgeuse, how could there be so much? Now, analysing data from NASA's Hubble Space Telescope together with several other observatories, astronomers have concluded that Betelgeuse quite literally blew its top off in 2019, losing a substantial part of its visible surface and producing what they're now calling a gigantic surface mass ejection. This is something that's never been seen before. Of course, the Sun routinely blows off parts of its tenuous outer atmosphere, the corona, in events known as coronal mass ejections. But that's quite different to the Betelgeuse surface mass ejection event, which blasted off some 400 billion times as much mass as a typical coronal mass ejection. The monster star is still only slowly recovering from this catastrophic upheaval. The study's lead author, Andrea Dupree from the Harvard-Smithsonian Center for Astrophysics, says Betelgeuse is continuing to do some very unusual things, with its interior sort of bouncing around. These new observations are yielding fresh clues as to how red supergiants lose mass late in their lives, as their nuclear fusion furnaces start to burn out in the countdown before they explode as core collapse supernovae. The amount of mass loss significantly affects their fate. However, Betelgeuse's surprisingly petulant behaviour isn't evidence that it's about to blow up anytime soon. So the mass loss event isn't necessarily a signal of an imminent explosion. Dupree is now pulling all the data pieces she can gather together, looking at what she can from before, during and after the eruption, placing it all into a coherent story of this never-before-seen titanic convulsion of an aging star. The data includes new spectroscopic and imaging observations from NASA's Hubble Space Telescope, the Strela Robotic Observatory, the Fred L. Whipple Observatory's TRESS spectrograph, and NASA's Stereo A spacecraft. Dupree says Hubble's data was pivotal in helping to sort out the mystery. She says astronomers have never before seen such a huge mass ejection event from the surface of a star, and they don't really understand what's going on. It's all a totally new phenomenon that's being observed for the first time. But Hubble is allowing astronomers to observe Betelgeuse's surface details and its evolution in real time. It's thought the titanic outburst in 2019 could have been caused by a convective plume some 2 million kilometres across, which bubbled up from deep inside the star. It produced shocks and pulsations that blasted off a chunk of the photosphere, leaving the star with a large cool surface area under the dust cloud that was produced by the cooling pieces of photosphere. Betelgeuse is now struggling to recover from this injury. Weighing roughly several times as much as the Earth's moon, this fractured piece of photosphere sped off into space and cooled to form a massive dust cloud, big enough to block light from the star as seen by Earth observers. The dimming, which began in late 2019 and lasted for several months, was easily noticeable by backyard observers watching the star change brightness. Even more spectacular, the red supergiant's 400-day pulsation rate, one of its key characteristics, is now gone. Possibly only temporarily, but, well, who knows? This is all new territory. For almost 200 years, astronomers have been measuring the rhythm of this pulsation, as evident in changes in Betelgeuse's brightness, variations, and surface motions. Dupree thinks the star's interior convection cells, which normally drive this regular pulsation event, may be sloshing around inside the star like an unbalanced washing machine tub. The TRES and Hubble spectra suggest that the outer layers of the star may now be back to normal, but the surface is still bouncing around like jelly as the photosphere rebuilds itself. Though the Sun has coronal mass ejections that blow off small pieces of the outer atmosphere, astronomers have simply never witnessed anything this large before, and so they're fairly convinced that surface mass ejections and coronal mass ejections may be very different events. Betelgeuse is the brightest star in the constellation of Orion, representing the scorpion sting on Orion's shoulder. Located somewhere between 530 and 643 light-years away, depending on whose measurements you prefer, it's one of the largest and most luminous stars visible with the unaided eye from Earth. Commonly called Betelgeuse, don't say it 3 times, its original name before centuries of tortured mispronunciations started out as Ibdal Yaza, meaning the right hand of the big man in Arabic, the big man being Orion the Hunter. Betelgeuse began its life around 10 million years ago as a spectral type Ob blue star. Calculations of Betelgeuse's mass range from slightly under 10 to a little bit over 20 times that of the Sun, with around 100,000 times the Sun's brightness and around 1,100 times its diameter. In fact, Betelgeuse is so big, were it placed where the Sun is at the center of our solar system, its visible surface would extend out beyond the orbit of Jupiter, engulfing the orbits of Mercury, Venus, Earth, Mars, and the main asteroid belt. Red supergiants are the largest stars in the universe in terms of their volume, although they're not necessarily the most massive or luminous. After spending millions of years fusing hydrogen into helium in their cores, a star's core hydrogen supply eventually runs out, and the balancing act between the nuclear fusion process pushing out and gravity pushing inwards stops, and gravity wins. Now, the huge mass of the star crushing down onto its core under its own gravity causes a dramatic increase in core pressure and consequently temperature. Eventually, things get hot enough that it triggers what's called a helium flash, which causes the helium in the core to start fusing into carbon and oxygen. Now, at the same time, the contraction of the core means the hydrogen-rich region around the stellar core has moved down into the area where temperatures and pressures are hot enough for hydrogen fusion into helium to commence, creating a shell of burning hydrogen around the core. Meanwhile, the increasing core temperature results in an increasing level of luminosity, and the resulting radiation pressure from the shell burning causes the outer diffuse gaseous envelope of the star to expand hundreds of times beyond its previous radius. As the now bloated star's chromosphere or visible surface moves further away from its core, it cools down, turning redder, and hence the star has become a red giant. Stars like our Sun will eventually lose their outer envelopes, which continue expanding outwards as planetary nebulae. This ultimately exposes the star's white-hot stellar core as a white dwarf. However, stars like Betelgeuse, with masses more than 8 times that of our Sun, experience a very different fate. Unlike our Sun, because they have so much more mass, their fusion cycle doesn't end with helium fusing into carbon and oxygen. They have enough mass to fuse the carbon and oxygen in their core into progressively heavier and heavier elements through a different process, while shell burning around the core also fuses progressively heavier and heavier elements. So we have carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, nickel, and eventually iron. These stars have become supergiants. But no matter how big a star is, it can't fuse iron into heavier elements. And at this point, the star reaches the end of the line. Once again, that balancing act between nuclear pressure pushing outwards and gravity pushing inwards ceases, and gravity wins, and the star quickly collapses in on itself. Now, if they're between, say, 8 and 20 times the mass of our Sun, they'll produce a spectacular event called a core collapse supernova, and they'll end up as a neutron star. However, if they're more than 20 times the mass of the Sun, chances are the collapse will continue beyond the neutron star stage and they'll form a stellar mass black hole, a point of singularity of infinite density in zero volume, a place where the laws of physics as science understands them no longer apply. As for Betelgeuse, well, it's expected to explode as a core collapse supernova sometime soon, which in astronomical terms could mean tomorrow or it could mean 1,000,000 years from now. Whenever it happens, we'll notice, assuming the human race is still around. It'll temporarily outshine all the other stars in the galaxy, and it will be clearly visible in the day's sky from Earth. The last star to be seen by humans to go supernova in our galaxy was Tycho's star. That was back in 1572, and that was before the invention of the telescope. This is space-time. Still to come, could Earth's continents have come from outer space? And NASA's DAVINCI mission to explore the atmosphere of Venus. All that and more still to come on Space-Time. A new study suggests that Earth's continents could have been formed by material delivered in giant meteor impacts. The findings, reported in the journal Nature, are based on detailed studies examining the composition of oxygen isotopes in zircon crystals found in the Western Australian Pilbara region, which contains some of planet Earth's oldest continental crusts. The study's lead author, Tim Johnson from Curtin University, says the Earth suffered a high number of asteroid and meteor impacts during the first billion years of the planet's 4.6 billion year history. Johnson says the idea that continents originally formed at sites of giant meteoroid impacts has been around for decades, but until now there's been little solid evidence to support the hypothesis. By examining tiny crystals in the mineral zircon in rocks from the Pilbara Craton, which represent Earth's best preserved remnant of ancient crust, the authors found evidence for these giant meteorite impacts. Johnson says studying the composition of oxygen isotopes in these zircon crystals revealed a top-down process, starting with the melting of the rocks near the surface and progressing deeper, consistent with the geological effect of a giant meteoroid impact. He says the research provides the first solid evidence that the processes which ultimately formed the continents began with giant meteorite impacts similar to those responsible for the extinction of the dinosaurs, but which occurred billions of years earlier. Johnson says understanding the formation and ongoing evolution of Earth's continents was crucial, given that these land masses host the majority of Earth's biomass, all humans, and almost all of the planet's most important mineral deposits. These mineral deposits are the end result of a process known as crustal differentiation, which began with the formation of the earliest land masses, of which the Pilbara Craton is one example. Data related to other areas of ancient continental crust on the Earth appear to show patterns similar to those recognised in Western Australia. Johnson says he wants to test his findings on these ancient rocks to see if the model holds out.
So we know continents, continental crust, which is mainly made up of granites, these pale-coloured rocks that many of us have got on our kitchen surfaces, work surfaces. We know they've been around for 4 billion years or so, and some of that evidence is right here in WA. However, exactly how the continents came to be, how they first formed, is very poorly understood. Now, most people, I would wager, would say that there are competing models for how the continents first formed, but most people would favour internal processes. So, as you and your listeners will know, the Earth is very hot in its middle, and like any other bodies that have accreted, they started with lots of heat, and that heat has got to go somewhere, so it makes its way out from the core to the surface. And that's what we think is driving plate tectonics, which is operating today, and pretty much any active process that we can see operating on Earth, earthquakes and volcanoes and stuff. Now, some people would believe that the first continents formed by subduction, so much in the same way as they do today, where you have these rigid plates of oceanic crust that are in places diving underneath one another. As they get very deep, they get hot and they melt, and then they produce these granites, the continental crust. The other sort of end member internal model would be so-called mantle plumes, where you've got these blobs of heat that come from the core mantle boundary. The mantle is the layer in between the core and the crust on which we live. So the mantle plume is a bit like a lava lamp, if you're old enough like me to remember lava lamps, where you're getting these blobs of heat making their way to the surface. And when they get close to the surface, they cause massive amounts of melting and the production of a so-called oceanic plateau. So the sort of thing that we know is present beneath Hawaii and Iceland and other things like that. However, it's always seemed pretty plausible to me that we could be looking at an external origin for the continents. And people have been proposing this since at least the 1960s. That's the first paper that I could find. But I'm sure the idea has been around longer than that. But it's not really been taken up by the scientific community because of the lack of any concrete evidence. And I think in this research we found some evidence that might suggest that this giant impact theory is actually right.
So this is different from material floating on the surface, which is sort of what we think of when we think of granitic material, the continental crust.
No, it absolutely is. But to actually make continental crust is a bit more involved. You need a two-stage process. So we know that the primitive sodium-rich granites that we find absolutely everywhere around the planet in the really ancient rocks, we know that they were formed by partial melting of basaltic rocks, but basaltic rocks that have been hydrated. So again, basalts are these dark volcanic rocks that come out of places like Hawaii and Iceland and other places as well. And providing you can add water to those things, you melt them to make these granites. And the granites are much less dense, and as you say, they float. But the question is, how do you make those really big blobs of basaltic volcanic rocks that can then evolve into become the granitic continental crust? And that's really what we are looking at, or we think we found evidence, this very first massive input of energy that gets everything kick-started.
And this is where zircons come in. They're so important, aren't they, to studying really ancient geology?
Absolutely they are. So zircon is a beautiful mineral. It occurs in many of these granites that make up the continental crust. They're very small, the grains. They're about the width of a human hair or so, but they're incredibly robust, physically and chemically robust. So the earliest material we know about on Earth are the so-called Jack Hills zircons, and they are getting close to 4.4 billion years old. So that's an awful long time for a mineral to hang around. So they are a robust record, or our only record of really what was going on in the early Earth. Now, the great thing about zircon, one of the great things, is that when it grows, it incorporates lots of uranium into its structure. And as we all know, uranium is a very heavy element. It's unstable, so it decays to various isotopes of lead. Now, with instrumentation we've got at Curtin, we can fire various beams at these tiny zircon grains, and we can measure those isotopes, and we can get a really quite precise age on those grains.
That's because the uranium is decaying into lead at a set rate.
That's right, yes. So there's actually two decay schemes where uranium decays to two different isotopes of lead. So two different isotopes of uranium decay to two different isotopes of lead, which gives us a check on our sums, basically. And if both of these things give the same age, both of these decay schemes give the same age, you can be pretty confident that your age is right and not some artifact. So if you're analysing lots of zircon grains, as we did, you've got a beautiful timeline of the processes that they record. Now, another thing that zircon and most other minerals contains is lots of oxygen. And we can measure two of the isotopes of oxygen, oxygen 18 and oxygen 16. Oxygen 16 is the common form of oxygen. And without getting into too much detail, that isotopic ratio tells us something about the environment in which those zircons originally crystallized. Now, in the Pilbara, there is the very, very oldest zircon grains we've got, which is the earliest record of what could have formed the Pilbara in the first place. They have about a third of the zircons have what we say is isotopically light compositions. And the only way of forming them, or at least the only way we think or the most plausible way of forming them, is that they represent, to get these isotopically like compositions, you have to be melting something close to the surface, so within the uppermost few kilometres of the Earth. Now, anybody walking around on the Earth now and then would notice that it's not particularly hot. So to actually melt the surface, to cause this extensive surface melting, and then the pattern becomes successively deeper thereafter, is entirely consistent with this giant impact theory. So the first thing that's happening is you're smashing an asteroid into the surface of the Earth, so you're causing massive amounts of melting at the surface, and then as the whole system evolves, it becomes deeper and deeper. And that's entirely what the pattern of the Pilbara data is showing, and tantalizingly, it looks like that similar pattern you can see elsewhere. So it's this top-down pattern where you're starting from shallow to deep, which really gives us some confidence that the giant impact theory might be right, because the main alternative, which is the Mantle Plume model, would start from very deep within the Earth and get progressively shallower. So it's the opposite of the trend we actually see in the data.
And this giant impact model, it matches up with things like the late heavy bombardment.
It does, yeah. So when you look at the Pilbara craton in detail, as other people have done, you can find these layers that we call spheroidal layers. So they are high energy impact deposits, and we can date those deposits as well. And for the Pilbara, we would argue that we had this giant impact at around 3.5 or 3.55 that eventually went on to become the Pilbara. But we can also see in the data these departures to isotopically light zircon, and they coincide beautifully with the age of these spheroidal beds. So we've got a direct link between the data and what it might mean.
Does that also help explain why the Pilbara is so iron rich?
That's another interesting aspect, yes. So not all, but in most of the samples that we're finding these really light isotopic compositions, the rocks in which they occur are very iron rich, as you say. And exactly why that is unknown, but we would argue that it's exactly what you would predict if you were crystallizing a terrestrial magma ocean. So again, as your viewers will be more expert than I, and many of them, the Earth is thought to have collided with a Mars-sized object here to form the Moon 4.5 billion years ago. So the Moon would have formed from that entirely molten mass, and the Earth would also have been completely molten to some depth. Whether it's right the way to the core, who knows, but a significant amount of the Earth would have been entirely molten. And then if you slowly cool that, it crystallizes from the inside out. So it's basically a basaltic composition, and you start crystallizing things like olivine and orthopyroxene, and then the residual melts. What's left over as it cools gets successively richer in iron. So that's a nice little bit of a side story, really, that we might be impacting the results of the crystallization of the terrestrial magma ocean that would form when the Moon did.
So the key now, I guess, is looking for...
Well, the next stage of what we'd really like to do, so we've written some proposals to go and look at ancient rocks from elsewhere on the planet. So Pilbara is the most pristine example of this really ancient continental crust we have. But you can find fragments of it absolutely everywhere in Canada and Greenland and Europe and South America and wherever.
And South Africa too, yeah.
Precisely, South Africa. Barber's a beautiful place. So what we would like to do is go and recollect some of those samples and apply the same filters to the analyses that we've done for the Pilbara data to see if, as the data seems to hint at elsewhere, there is evidence of this giant impact model elsewhere. And perhaps, who knows, the giant impact model might be applicable to all continents.
That's Associate Professor Tim Johnson from the School of Earth and Planetary Sciences at Curtin University. And this is SpaceTime. Still to come, NASA releases details of its new DAVINCI mission to Venus, and bound for the Moon, NASA's massive Artemis 1 rocket rolls out onto the launch pad in preparation for its maiden flight. All that and more still to come on SpaceTime. NASA has released details of its proposed new DAVINCI mission to the planet Venus. Slated for flight on a United Launch Alliance Vulcan rocket in June 2029, the Deep Atmosphere Venus Investigation of Noble Gases Chemistry and Imaging, or DAVINCI mission, will be the first to study Venus using both spacecraft flybys and a descent probe. A NASA report in the Planetary Science Journal describes how the DAVINCI descent probe will slowly drop through the layered Venusian atmosphere in mid-2031, recording changes in atmospheric chemical composition and environmental conditions all the way down to the planet's surface. It will also provide the first descent imaging of the mountainous highlands of Venus, while mapping their rock composition and surface topography at scales simply not possible from orbit. The mission will measure undiscovered trace gases in the deepest atmosphere, including key ratios of hydrogen isotopes, components of water that will help reveal the history of water either as liquid water oceans or as steam within the early atmosphere. The mission's flyby probe, called the Carrier Relay and Imaging Spacecraft, or CRIS, has two onboard instruments that will study the planet's clouds and map its highland regions during flybys. DAVINCI will paint a picture of the layered Venusian atmosphere and how it interacts with the surface of the mountains of Alpha Reggio, which is as big as the state of New South Wales, around twice the size of the state of Texas. DAVINCI's principal investigator Jim Garvin from NASA's Goddard Space Flight Center in Greenbelt, Maryland, says these measurements will allow scientists to evaluate historical aspects of the atmosphere, as well as detect special rock types at the surface such as granites, while also looking for telltale landscape features that could show evidence of erosion or other formational processes. DAVINCI will make use of 3 Venusian gravity assists, which will save fuel by using the planet's gravity to change speed and direction. The first 2 gravity assists will set CRIS up for a Venus flyby, performing remote sensing in the ultraviolet near-infrared. The 3rd Venus gravity assist will set the spacecraft up to release the probe for entry, descent, science and touchdown, plus any follow-up transmissions to Earth. Scientists estimate the first flyby of Venus will be about 6.5 months after launch, and it will take 2 Earth years to get the probe into position for entry into the atmosphere over Alpha Reggio under ideal lighting conditions, with the goal of measuring the landscapes of Venus at scales ranging from hundreds of meters down to less than 1 meter. Such scales will enable lander-type geologic studies of the mountains of Venus without actually requiring a landing. Once the CRIS system is about 2 days away from Venus, the probe flight system will be released, along with a 2-meter-wide titanium probe safely encased inside. The probe will begin to interact with the Venusian upper atmosphere at an altitude of around 120 kilometers above the surface. But it won't commence its science observations until after jettisoning its heat shield. That'll be at about 67 kilometers above the surface. With the heat shield removed, the probe will then begin ingesting atmospheric gas samples, providing detailed chemistry measurements of the sort that have been made on Mars with the Curiosity rover. During its slow hour-long descent down to the surface, the probe will also acquire hundreds of images as soon as it emerges from under the clouds. That should be at around 30,000 meters, 30 kilometers above the local surface. If all goes according to plan, and the winds don't blow it off course, the probe will touch down somewhere in the Alpha Reggio Mountains. Now, if it survives the touchdown, and it will be hitting the ground at around 12 meters per second, there could be up to around 18 minutes of bonus operations and measurements of the Venusian surface. Of course, the problem is, no spacecraft have survived long in the Venusian atmosphere, or for that matter on the surface. The Russians have tried, sending back tantalizing images of the surface and readings lasting a few minutes before systems all failed. The problem is, while Earth and Venus are considered sister planets, both roughly the same size, the same mass, made out of the same material and formed in the same part of the solar system under similar conditions, Venus and Earth have turned out very differently. Temperatures on the Venusian surface are hot enough to melt lead, more than 460 degrees Celsius. Atmospheric pressure at the surface is 100 times greater than at sea level on Earth, and it's an atmosphere heavily dominated by carbon dioxide. When it does rain on Venus, it rains sulfuric acid, and the snow on the mountain tops is metallic. So anything landing on Venus will get crushed, cooked, broiled, boiled, and burnt. This report from NASA TV.
Launching in 2029, the DAVINCI mission, named after Leonardo da Vinci, is designed to address fundamental questions about the origin, evolution, and composition of Venus. During 2 gravity-assist flybys, Da Vinci will study the cloud tops in ultraviolet light, tracking cloud patterns as they change with time and analyzing signatures of mysterious chemicals that absorb ultraviolet light. Both flybys will also examine heat emanating from the Venus surface on the planet's night side. We will look for geological clues of this planet's mysterious past to paint a global picture of surface composition and the evolution of the planet's ancient highlands. 7 months after our second flyby, Da Vinci will release its atmospheric descent probe. The spacecraft will watch its probe enter Venus's atmosphere over the course of 2 days. The probe will take about an hour to fall through the atmosphere, taking measurements and snapping images down to the surface. These measurements include profiles of composition, winds, temperature, pressure, and acceleration. Key gases will be measured to help us understand how Venus formed and evolved. Some of these measurements may reveal chemical signatures of ancient water. With our suite of measurements, Da Vinci will provide new insights into Venus's atmosphere's complex composition, structure, and chemistry. As the probe nears the surface, its descent camera will capture breathtaking bird's-eye views of the mysterious terrain known as the Alpha Regio Tessera, possibly revealing evidence in the rocks that water once flowed across the Venusian surface. These up-close images of the surface will provide new insights into geologic processes and will help us to understand what it might be like to stand on the Venus surface. An oxygen-sensing student collaboration experiment will shed light on the role of this gas in the Venus atmosphere. The discoveries that emerge from this diverse dataset will tell us whether Venus was truly habitable, and the story we reveal at Venus will reach even beyond the solar system to analog exoplanets that will be observed with the James Webb Space Telescope.
This is Space Time. Still to come, NASA's Artemis 1 moon mission rolls out onto the launch pad, and later in the science report, a new effort using cloning to try and bring the Tasmanian tiger or thylacine back from extinction. All that and more still to come on Space Time. NASA's Artemis 1 SLS Moon rocket is back at Space Launch Complex 39B at the Kennedy Space Center in Florida as preparations continue for its historic maiden flight later this month. Crowds began building up around Cape Canaveral as the massive 98-metre tall rocket undertook its historic 7-kilometre 10-hour overnight rollout from the massive vehicle assembly building out to the launch pad, arriving at dawn. The first of 3 launch windows for a flight this year will be on August the 29th. The unmanned test flight, which will last some 42 days, will travel beyond the moon, deploying a number of microsatellites and CubeSats along the way. Replacing the crew will be 3 mannequins loaded with sensors to measure radiation and vibrations. The mission's Orion capsule will then return to Earth, entering the atmosphere faster than any other human-rated spacecraft ever, eventually splashing down in the North Pacific Ocean. Now, if successful, it'll be followed by the Artemis 2 mission, slated for May 2024, and that will be the first manned flight carrying a crew of 4 around the moon and back. That in turn will be followed in 2025 or possibly 2026 with the Artemis 3 mission, the first manned flight to the lunar surface since Apollo 17 back in 1972, more than half a century ago. Once in lunar orbit, the Artemis 3 Orion capsule will dock with a pre-positioned SpaceX Starship HLS lander. 2 of the Orion crew members will then transfer to the lander and travel down to the lunar surface, touching down near the South Pole for a week-long stay, undertaking science observations and collecting samples. Scientific equipment and supplies will be pre-positioned at the landing site. And NASA assures us this time humans will be back to the moon to stay. An orbiting lunar space station, the Gateway, will be positioned in the second half of the decade, And eventually the experiences learnt by working on the Moon will be used for the first manned missions to Mars. And they'll take place sometime in the 2030s. This report from NASA TV.
Through Artemis, the twin sister of Apollo, we are returning to the Moon. Orion, the only human-rated spacecraft in the world capable of deep space travel. And now, the Space Launch System, NASA's most powerful rocket since the Apollo era, stands ready. Having undergone and passed numerous tests, the time has come to complete the journey. With hardware originating from every state in the nation and from partners around the world, Artemis 1 will be the first flight test of each of these components now assembled together. Two solid rocket boosters will provide more than 75% of the thrust necessary to leave Earth. Each booster stands 17 stories tall, a full segment more powerful than the SRBs of Shuttle. Together, these boosters are capable of 7.2 million pounds of thrust and will burn for the first 2 minutes of flight. The core stage, at 212 feet, is the tallest rocket stage NASA has ever built. With the rocket's flight computer secured inside, the core stage is designed to hold 2.3 million pounds of fuel. The 196,000 gallons of liquid oxygen and the 537,000 gallons of liquid hydrogen will combine to provide 8.5 minutes of propellant to the 4 massive RS-25 engines mounted below. As proven workhorses of the shuttle fleet, each RS-25 engine has a legacy all its own. Together, these 4 engines provide 2 million pounds of thrust, and with the SRBs, are capable of pushing Orion to a speed of 17,000 miles per hour. The interim cryogenic propulsion stage is a 45-foot tall upper stage that offers Orion nearly 25,000 pounds of thrust. Performing 2 separate burns, the ICPS will first raise Orion's orbit and then, later, propel it out on a trajectory to the Moon. The ICPS is powered by a single RL-10 engine that will perform these 2 burns. This storied engine has propelled robotic missions to every planet in the solar system, including Voyager 1 and Voyager 2, the first space probes to reach interstellar space. Orion's service module, provided by the European Space Agency, is the powerhouse that fuels and propels Orion in space. It stores the spacecraft's propulsion, thermal control, electrical power, and critical life support systems, such as water, oxygen, and nitrogen. Orion's crew module is the pressurized segment of the spacecraft, where future crews will live and work on journeys to the Moon. Capable of accommodating 4 crew members for up to 21 days, this capsule includes state-of-the-art avionics, innovative crew systems, and the largest heat shield of its kind for entry back into the Earth's atmosphere. Positioned at the top of Orion is the Launch Abort System, designed to pull the crew to safety in the event of an emergency, on the pad or during launch. 3 solid rocket motors can activate in milliseconds, accelerating from 0 to 500 miles per hour in 2 seconds to propel Orion and crew safely away from the rocket. Now fully assembled, Artemis 1 stands at 322 feet. Artemis is no longer a series of separate parts and programs. United together, this is the first of Artemis's arrows, capable of ushering in the next chapter of human lunar exploration. Only together, this mighty system represents all that is possible, all that we are capable of when united around a stunning vision, with each component playing its part in a grander effort. We, the people of NASA and our partners, we, the people of the Artemis generation, all around this beautiful world, will bear witness to what we are capable of. Together, we are going back to the moon.
SpaceX have launched a new moon probe for South Korea. The flight was launched aboard a Falcon 9 rocket from Space Launch Complex 40 at the Cape Canaveral Space Force Base in Florida. The spacecraft, named Denori, Korean for Enjoy the Moon, is on a low-energy ballistic capture flypath to the moon, which requires no delta-V and allows the probe to quite literally fall towards the moon. It should arrive in lunar orbit insertion in December. The solar-powered spacecraft will orbit 100 kilometers above the lunar surface for a year, gathering geological data. The probe is carrying 6 scientific instruments, including a camera for NASA that'll search for water ice in the permanently shadowed crater floors that never see sunlight. Other instruments include a lunar terrain imager, a wide-angle polarimetric camera, a magnetometer, a gamma-ray spectrometer, and what they're calling a delay-tolerant networking project. Basically, it's designed to undertake a range of communications experiments. The $180 million mission is South Korea's first to the moon. Back in June, South Korea successfully launched a package of satellites into orbit using its own rocket for the first time. The country plans on landing a probe on the lunar surface in 2030. The mission joins spacecraft from the United States, China and India currently operating on or around the moon. Russia has launched an Iranian spy satellite into orbit, further cementing a new axis of evil between the two despotic nations. The Islamic Republics maintain close ties with Moscow and has refrained from any criticism of the Russian invasion of Ukraine. The 600-kilogram Kayam satellite was launched aboard a Soyuz 21B rocket from the Baikonur Cosmodrome in the Central Asian Republic of Kazakhstan. The Washington Post quoted Western intelligence officials as saying that Russia plans to use the satellite for several months to assist in its war efforts against Ukraine before allowing Tehran to take control. However, Tehran insists the Islamic Republic would control the satellite from day one due to the satellite's encrypted algorithms. The growing international isolation of Russia under the weight of Western sanctions over Ukraine has seen the Kremlin seek closer ties with nations like China, Iran and North Korea. Ironically, Iran is currently negotiating with world powers, including Moscow, over its growing secret nuclear weapons program. Tehran insists its nuclear program is for peaceful power generation only. However, it continues, either through its own efforts or espionage, to develop technologies which can only be used for nuclear weapons. This is SpaceTime. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.